Good morning, everyone. My name is Mod Hanafi, and today I am honored to present our research paper, Decarbonizing Earthmoving Machinery, Design and Prototype of a Fully Electric Linear Actuated Excavator. In this presentation, we will walk you through how we designed, modeled, and prototyped a novel, zero-emission subcompact excavator. Our design entirely bypasses traditional fluid hydraulic systems in favor of high-force electromechanical linear actuators, presenting a clean, precise, and highly energy-efficient alternative for modern construction. Let's begin with why this transition is critical. The global construction industry is under immense pressure to reduce its massive carbon and acoustic footprints, particularly in urban areas. This alignment is driven by national frameworks like Malaysia's National Fourth Industrial Revolution Policy and the New Industrial Master Plan, NIMP, 2030, alongside global commitments under the Paris Agreement. While battery electric powertrains are increasingly standard, the key bottleneck remains the hydraulic actuator system itself. Traditional diesel hydraulic setups suffer from low powertrain efficiency due to persistent heat dissipation, fluid friction, and severe parasitic losses, meaning they consume energy to maintain system pressure even when completely idle. Furthermore, hydraulic line leakage poses a constant risk of soil and groundwater contamination. To address this, our research explores a complete shift to an oil-free, electromechanical architecture. On the left, we see the traditional limits. Hydraulics suffer from severe parasitic power losses because they must maintain high pressure during idle phases. They present high maintenance overhead with failure-prone hoses and valves, and they carry a high risk of soil contamination. On the right, we highlight the electromechanical benefits. Our system achieves zero localized emissions, making it ideal for indoor or quiet urban zones. More importantly, it features direct power conversion. Energy is drawn strictly on demand when the actuators are actively moving. This setup also provides clean, electronic, closed-loop feedback for highly precise, automated operation while simplifying maintenance by completely eliminating fluid lines. Now, let's look at the actual structural design of our subcompact prototype. As displayed in the CAD assembly shown on the slide, the mechanical layout of our mini-electric excavator replaces conventional hydraulic cylinders with high-force electromechanical lead screw actuators to drive the boom, arm, and bucket linkages. By utilizing lead screws, our design leverages their low back drivability. This mechanical characteristic is crucial because it allows the excavator to lock its links and hold static loads with near-zero energy consumption. To distribute loads safely, we implemented a parallel linkage configuration. Structurally, the main chassis is fabricated using robust 1" by 3" mild steel hollow rectangular tubing for structural rigidity, while the upper arm is built from lightweight 1" by 2" aluminium hollow rectangular tubing to minimize non-load bearing weight and improve overall responsiveness. Let's dive into the control system and electrical architecture that coordinates this prototype. The brain of our excavator is an Arduino Uno microcontroller. It processes real-time input signals from the operator joysticks and performs the inverse kinematics calculations on the fly to generate precise, coordinated pulse width modulation (PWM) motion profiles. To bridge the gap between low-power logic and high-power physical movement, we integrated two L298N dual H-bridge motor drivers. These act as solid-state relays, safely distributing dynamic, bidirectional current to the three actuators. The entire system is powered by a shared, direct grid-tethered 12 volts DC battery supply, which ensures a steady current buffer to handle rigorous excavation stresses while maintaining a strict common ground across all components to eliminate signal drift. This bar chart visually underscores the efficiency benchmarks we just reviewed. As you can see, partial load hybrid architectures struggle to cross the 33% efficiency mark, and advanced pump control systems peak at around 39% savings. The all-electric linear lead screw configuration achieves an extraordinary 66.1% saving. By removing fluid dynamics entirely, we eliminate mechanical valve throttling and hose expansion losses. This proves that all-electric, line-actuated mechanisms effectively double the efficiency gains of conventional electro-hydraulic hybrids. Let's explore the physical mechanism behind this 66.1% efficiency leap. Traditional hydraulic excavators constantly waste power because fluid must remain pressurized even when the arm is completely still. In contrast, our electromechanical lead screws draw power strictly during coordinate translation. Once the boom, arm, or bucket reaches its target angle, the low back drivability of the screw naturally locks the mechanism in place. This allows the prototype to maintain its static physical posture with absolutely zero power draw, completely decoupling holding power from continuous energy expenditure. Here is the prototype design and mechanical layout of our electric mini excavator. The CAD models highlight how the electric actuators integrate with the chassis. Key dimensions include a 52 cm rear height, a 50 cm vertical mast, and a 60 cm boom assembly, optimizing compact strength and fluid-free operation. This is the result for range of motion for each links. Our prototype achieves an excellent motion range. The boom link pivots between 62 and 93 degrees, the arm link ranges from 70 to 130 degrees, and the bucket rotates from 94 to 139 degrees. This precise mechanical design ensures versatile and efficient excavation. For our electric excavator to mimic the smooth, intuitive operation of a human operator, the control system must translate Cartesian joystick coordinates, specifically the desired X and Y position of the bucket, into precise angular adjustments for the joint links. To achieve this, our Arduino Uno executes the inverse kinematics equations shown on the slide in real time. Equation 1 calculates the joint angle θb for the boom link using the cosine rule on the coordinate vectors. Equation 2 uses the arctangent of the coordinates to solve for the arm joint angle θa. For example, to dig a flat, straight trench at a consistent 26.7 cm depth, the boom and arm angles must move dynamically and in perfect synchronization, decreasing from $93 carat, circ, $, to $74 carat, circ, $, on the arm as calculated by these geometric models. Next, let's look at the maximum excavation depth. The prototype reaches a standard digging depth of 26.7 cm. However, as we optimize the system and decrease the arm link angle, the geometric reach extends significantly, allowing the excavator to achieve a deeper maximum digging depth of 36.5 cm. In conclusion, our fully electric, linear actuated prototype successfully demonstrates the feasibility of an oil-free construction vehicle. We achieved stable, coordinated motion with zero localized emissions and zero risk of oil contamination. In terms of physical performance, our current prototype achieves a range of motion of 31 degrees for the boom, 60 degrees for the arm, and 45 degrees for the bucket, allowing for a maximum digging depth of 36.5 cm. While these parameters represent a 61% reduction in the range of motion compared to conventional commercial excavators, this prototype serves as a vital proof of concept. Our future engineering focus will involve redesigning the linkage geometries, optimizing mounting locations, and selecting longer stroke vectors to scale these ranges of motion up to commercial standards. Thank you very much for your time. I am now open to any questions you may have.